Right now, spacecraft communicate and send data back and forth using radio frequencies, much like your car radio. Well, the OPALS investigation is proving that it can now be done with lasers. I caught up with Matt Abrahamson at the Jet Propulsion Laboratory to learn why OPALS may be the gem scientists are looking for.
We launched up to the space station in April 2014, and we're a technology demonstration mission for laser communications technology that's sending data over laser beams rather than radio waves.
Why is that so important?
Well, basically a laser beam is much more focused than a radio wave, so for the smaller amount of power that's transmitted, you can transmit much more information. It's also at a higher frequency than radio waves, so you can pack more bits into that same data stream. So you can get data rates that are 10 to 100 times faster than the potential for radio waves.
So we've practiced this a few times. We've seen it in action. How did it work?
Oh, it worked great. We got up there in April, as I mentioned. We started operating in May. Everything checked out as expected. Went through a few checks to make sure we can point, because one of the major technologies of this is to demonstrate that we can point within a few microradians of the target ground station. And we had our first success on June 5th, where we were able to actually transmit a high-definition video from the space station on OPALS down to our ground station in Table Mountain, California.
So how does that work? Is there crew involvement with this, or is it just strictly from the ground?
There's no crew involvement. We're an external payload, so we sit on the outside on Express Logistics Carrier 1, and everything's ground commanded from JPL. We send the commands from there. They go over to Marshall Space Flight Center, then to Johnson Space Flight Center, to White Sands, up through TDRS, all the way over to our payload in a matter of a few seconds, which is kind of incredible. So we command each step in the process to prepare for this transmission, and during the actual time period of the transmission, which is about 2.5 minutes when we pass over the ground station, everything's automated at that point. So we have this closed loop tracking algorithm that will track our ground station and transmit that video down to the ground.
It's the story of an endless search to serve the communications needs of America. Why the hurry?
So when we transmit things, you transmitted a video. Are you trying to transmit several things at once, or is it one at a time? How does that work?
It's one video, and we'll continuously loop it. So there may be dropouts during the middle of the transmission. Typically we're transmitting at 50 megabits per second, and our standard video is about 175 megabits. So every 3.5 seconds you get a new copy of the video. But you could have dropouts in the middle, so we have an algorithm that if you do have a few packet dropouts, when we reconstruct it on the ground, you can take different portions of the video from different packets that were received and reconstruct one video. Now in practice, it worked much better than expected, so our bit error rate was so low, it seemed like every copy, we got the full copy. There were a few instances where we hit clouds, and if you hit a cloud with the laser, you have a dropout. So we did have a couple instances where you had 10 seconds of dropout, but we'd have enough of the video transmission to reconstruct a complete video at the end.
How does this translate to long duration missions? This is what we're headed toward, right?
Yeah, that's right. So I think this is really important for deep space. From JPL's perspective, we'd like to put one of these on a Mars orbiter or even a Mars rover. And then that really increases the bandwidth of the amount of science data you can get back from the surface of Mars. Instead of taking snapshots of images, you could take video data and send that back to Earth. You can't do that right now. It also will be a big game changer in terms of manned spaceflight. We're going out to deep space, even to the moon. You want to have as much bandwidth as possible to talk to those astronauts, and you're going to need Lasercomm for that.
So what's next for OPALS?
Well, we're going to be on the station through February 2016. That's our current decommissioning date. And we have a few more demonstrations that we're looking to do. We just completed one, which was an adaptive optics experiment. In that experiment, we took a test bed that would take the OPAL signals that was received at the telescope, and it corrects all the atmospheric distortion that occurred as it was transmitted down. We're able to couple that into a fiber optics cable, and that just demonstrates that we're able to take this signal and transmit to fiber optics cable, possibly for transmission out to other ground stations. That was an important technology to test out. The next thing we'll be testing is a platform characterization experiment. That's an attempt to try to measure the vibration or the shaking on the space station. So it's not really optical communications, but based on our capabilities using lasers, we can get some useful measurements out of it. And then the fall timeframe, we're looking to do more transmissions to our foreign partners. That's ESA in the Tenerife, Canary Islands. That's DLR in Oberpfaffenhofen, Germany. NICT in Tokyo, Japan, and possibly CNES in Nice, France. So those will be nice collaboration to have before we end the program in February.
So it's important to have those other ground stations around the world.
That's right. I think both for collaboration and also looking at the variations you get with geometry variations. When we operate in California, the weather is fairly good for transmission of laser beams. When we operate in Germany, it's a little more challenging, and so we learn new things. It's also a much higher latitude in the planet, and so the link availability and when we can transmit is quite a bit different from transmitting in California. And so by looking at those variations, we're learning a lot about how robust this technology is for the future.